Well, one last thing in this section. Recall if a function is differentiable, then it must be continuous, and the same is true for multivariate functions. Chapter 13, section 4 of the theorem says, sufficient condition for differentiability if a function of x and y, where the partial derivatives f sub x and f sub y are continuous on an open region R, then f is differentiable on R. And if a function of x and y, this is theorem 13.5, is differentiable at a point x sub 0, y sub 0, then it must be continuous at that point. Okay? Here's an example to illustrate. The function f of xy is not differentiable at 0, 0 because it is not continuous at 0, 0. Now here's the function. F of xy is negative 3xy over x squared plus y squared. I think you can see the problem at 0, 0. Because at 0, 0, we have 0 over 0. That doesn't necessarily mean it's not differentiable, but we'll see, or that it's, sorry, that it's not differentiable, but we shall see that it is not. If we take the partial with respect to x and take the time to work this out, well, of course this is at the point 0, 0, so f of delta x 0 minus f of 0, 0 over delta x, we would get 0. Because we'd be putting in delta x for x and 0 for y, so we have a 0 numerator, and we have a delta x squared plus 0, so we have 0 over number, and therefore we get 0. So that's not a problem. I mean, this is 0, this is 0, so over some number that's approaching 0, so we still get 0. And if we do the same thing with respect to y, we get that same kind of result. You could put in the numbers 0, 0 into the function here, and we get a 0 numerator, and 0 times delta y, so it's still 0, minus 0 when you put in 0, 0 for x and y, and that over something that delta y is approaching 0 and delta y is going in for y, so this denominator isn't 0, it's just approaching 0. So you still get 0. So it seems like both partial derivatives exist and are 0. But if you look along the path where y equals x, and this was just a choose, like choose a different path, y equals x, notice that the limit as x. Now that would normally be xy, but we said y equals x, so I put a x in there where the y would be. As that goes to 0, 0 of this function, that means I'm putting in x for y. So this is negative 3x squared over x squared plus x squared, which is negative 3x squared over 2x squared, which is just negative 3 halves. And if we look along the path where y equals negative x, so notice, the limit as x negative x goes to 0, 0, well, golly, then we get positive 3 halves. So same idea. This is negative 3 times x squared, but it's actually negative 3 times negative x squared, because y is negative x, so it's 3x squared in the numerator. When we square negative x, we still get x squared, so we got 2x squared in the denominator, so we wind up with 3 halves. So the function is not continuous at the point 0, 0, hence it could not be differentiable at the point 0, 0, and I got a picture of it to show you the weirdness, what kind of a weirdness happens here. And I think you can see, if we went in one way along y equals 0 or x equals 0, we get 0 for this thing, but if you go in along, along the path y equals x, and we got bizarre results. See, there's kind of like a cliff there, if that makes sense. So that function is definitely not continuous, hence it could not possibly be differentiable. And for some reason or other it disappeared. There it is back again. Let me see if I can expand it. It might make it look a little better if I can. But you see the cliff happening there. And so obviously it's not differentiable there, but we could have been faked out into thinking that it was, especially when we looked at the partial derivative with respect to x at the origin and the partial derivative with respect to y at the origin, getting 0. But of course it wasn't continuous, so that couldn't happen. I'm trying to think of something that might be analogous. If you have maybe a function that's a straight line with a break at the point where x is 1, but the straight line has a slope of 1, and then you moved up, let's say 1 unit from that, and put another line with slope 1, but they're not connected to each other, then at the point where x is 1, that function wouldn't be differentiable, even though it looks like the derivatives are the same, kind of like ours did, right? But it's still not differentiable.